G'day and happy Good Friday to all of you out there. Today's problem we're going to look at links algebra and trig concepts together, which is quite nice and typical of what scholarship questions often do. We've got another guest lecturer, which is great for me, and he does a very good job of explaining the problem. So here it is. Discuss how the solutions of the equation depend on various values of m. So it's an equation that's got an algebraic structure to it, but it's also got a trig component in it. So on that note, I'm going to turn it over to Richard to discuss the solution, and I'm going to enjoy a hot cross bun. The chocolate, the Hershey's ones, recommend, very good. So over to you, Richard.
For this question, the most obvious way to approach it is with a quadratic formula like this, which I know all of you, of course, know and remember. So we can use this formula to write cos x in terms of n. And if you do that, and you do some math, some simplifying, you could write x in terms of n, right? So x equals 2n pi plus or minus inverse cos m plus or minus square root negative 3m squared minus 2m plus 1, where n is any integer. Right, but to discuss about the solution of x in this case would be a bit inconvenient because there's a lot of repeating part of x, right? So let's isolate the non-repeating part out of it and call it z, like that, right? So for z to have any solution, what's inside of the inverse cos has to be between 1 and negative 1, right? Otherwise, it doesn't make sense for the inverse cos, right? So there it is. And then what's inside of the square root also have to be bigger than 0. Otherwise, it will be imaginary, and having imaginary in cos doesn't make sense. So those two are the two conditions that have to be fulfilled for z to have any solution. Right, so if you solve for the thing on the right, that is not very difficult, right? It's just a upside down parabola, and then if you solve for it, you will find out that negative 1 smaller than m smaller than a third, smaller or equal than a third. Right, but the thing on the left is a bit trickier. So I did some math on some paper, and this is what I did. I solved for n plus or minus square root negative 3m squared minus 2m plus 1 equals negative 1. And I got m equals 0 and m equals negative 1 as my solution. And then I also solved for m plus or minus square root equals 1. And I got m equals 0 as my only solution, right? But that still doesn't give me much of an idea of what's the constraint on n actually is for z to have a solution or multiple solutions. So to do that, we have to. So for the square root part, we know that the inside of the square root is an inverted parabola, right? And once we put that parabola into a square root, the bottom part goes away, right? Because it's imaginary, and only the top part remains, and it will kind of look like a half semicircle. Actually, I'm not sure if it actually is half circle, but that doesn't matter, right? So that would be like the graph shown on the top left of the screen, right? And as we have solved before, the inside of the square root is greater than 0 when m is greater or equal to negative 1 and smaller or equal to a third, right? So that's where the two endpoints got from, a third and negative 1 and 0, right? And we also know that the y equals m part is just a straight line, right? Because it's just y equals m, right? So once we add the square root part and the m part together, we would kind of get a ellipse. Right, I'm not sure if that actually is ellipse, but that doesn't matter. Right, as shown on the right of the screen, we have 1n at 1/3, right? Because m is also y is also a third, but the thing inside the square root 0. And then we have another point at -1, -1. But from the previous slide, we also know that when the whole thing equals -1, m equals 0, right? So that's why the curve also goes through 0, -1. And we also know from the previous slide that when the whole thing is 1, m also solves to 0. So there it is. The curve also goes through 0 and 1, right? So I have the same graph, but except this time it's from decimals and it looks a lot better. The black part is the part with the positive square roots, and the red part is the part with the negative square root, right? So, as we mentioned on the first slide, for g to have a solution, this thing has to be between 1 and -1, or in this case, y have to be between -1 and 1, right? So, let's start. At m equals 1/3, right? What's inside of square root 0? So there's only one solution, and that solution is indeed between 1 and -1, right? When m is smaller than 1/3 but greater or equal to 0, right? There are two solutions, right? One of them at the top, the black part, when for the positive square root, and another one for the negative square root, and both of them is still in the closed interval of 1 and -1. Right, and then we keep going. We go to the negative part. When m is smaller than 0, but greater or equal to 1, greater or equal to -1, we only have one solution. Because now, the negative square root part goes below -1, and therefore only the positive square root counts. So, here are the answer to the question. Right, as inverse cos of anything would be smaller or equal to pi or greater or equal to 0, all solution for g is essentially all solution for x between 0 and pi. Right, so from before, we know that for m equals 1/3, there is one solution for x between 0 and pi. For 0 smaller or equal to than m, smaller than 1/3, there are two solutions for x between 0 and pi. And for m smaller than 0 but greater or equal to -1, there is one solution for x between 0 and pi. Otherwise, there are no solutions.
Thanks for that awesome mathematics there, Richard. You're still the man. There's no extension question today because I know that you guys are all busily working on your assignment. Maybe have a second hot cross bun instead. See you later.